a collaboration with Damiano and Brigo from Imperial College. And as I said, the subject is stochastic filtering. I'll introduce and motivate the subject area of stochastic filtering first of all, and then try and show you how information geometry is useful. So the essential problem in stochastic filtering is, given a system which obeys some random process, or perhaps it obeys a deterministic process that's too complicated for you to model, so you model it stochastically. You have such a system, and you want to work out what the current state of that system is, or guess the state of that system from your measurements. But those measurements themselves might be imperfect. So that's the sort of general problem. And an example of the way you might want to do that is, I've gone for estimate the position of the car. In the first draft of my slides, it said estimate the position of a rocket. And that's the sort of history of the subject. It used to be very big in the Cold War. People would try and work out where the intercontinental ballistic missile was so that they could shoot it down. That was the main motivation of the subject. The Cold War ended, and so everybody moved into financial mathematics instead. So no communism, they could make money. And so the problem changed to something like, I've given the example of estimating the volatility of the stock, given current option prices, or it could just generally be, given market data, try and estimate underlying economic variables. And the aim there is, one has to model of the true state of the world, and if you can gain insight into the true state of the world, then hopefully you can profit from that. There are other applications. If you don't like war and you don't like money, you might like weather forecasting, oil extraction. There are lots of applications. One thing I should point out though, is a feature of this is that you want to make the decision online. So you want to, as the processes occur, estimate the current state. There's a very different problem called smoothing, which is after the entire simulation is finished, try and work out what actually happened. And the key is we want to work out things online. And that changes the nature of what's an acceptable solution. We want to calculate it fast. So although we know in principle algorithms to solve the filtering problem, if they're slow, they're fairly useless. Having said that, it depends a bit on the application. If you're trying to estimate the position of a car or a rocket, you probably want to be incredibly fast. Stock market, maybe not quite as fast, and the faster the better. And if it's weather forecasting, well, once a day will do. So, different problems, different algorithms are needed. And my main interest actually is in the financial mathematics. So here's a mathematical formulation of the problem. And I've written two stochastic differential equations. So the first equation for x is the state of the system. So it evolves essentially following some vector field given by f of x. So based on its current position, some vector field, it follows that. But there's also the second term involving dw. And w is a Brownian motion. It's a random noise. And so the first term says follow a vector field. The second term says except you're perturbed by some noise. The second equation is our measurement of the system. And our measurement is based on the current state of the system. That is mostly what changes the current measurement. But again, it's perturbed by another random noise. These equations, they might as well be vector equations, but I've simplified them. I've written them as scalar equations. It makes practically no difference. The question one wants to answer is, we can never find out what x is, but we can try because we know y is a noisy measurement, but we can try and work out the probability distribution for x, given the values of y that have happened so far. So that's the first question, and that question's solved, but was solved a long time ago. And the solution is this Kushner-Stratonovich equation. There are actually two solutions. I could put it the Zakai equation, which is essentially equivalent, but I've decided to run with this one. And it says that the probability distribution P evolves according to this stochastic partial differential equation. And there are two terms. So I'm trying to get to pen as well. No, very much. So the term involving this curly L, is the diffusion operator. So that's essentially saying that without any measurements, great, thank you. Which button do you press? Red one. Is it on that? Yes. Brilliant. No, I'm going that way as well. Right, so this term involves essentially a heat kernel, something like a heat kernel. And what that's saying is if we don't measure the system, the probability distribution diffuses and we become less and less certain about where it is. Whereas this term represents our measurement, and this is a correction. So there are two competing forces. One's making the probability distribution become more diffuse, and the other one is sharpening it up. And that's the solution for the probability density. The only problem is that that's a partial differential stochastic equation. Being a partial differential equation, that means it's infinite dimensional, and that means it's very difficult to solve, especially if you want to solve it online. Yes, I've described what the terms mean here, but let's just move on. So the real question now is how can we approximate this efficiently? And efficiently means depending upon your problem. Different people have different ideas, but how can I do it in terms of financial math is what I'm interested in. And the essential idea is quite straightforward, so I'll draw you a picture. If we've got a differential equation, we can think of that as being defined by a vector field. So that's some vector field in space. And we can try and solve the problem by restricting that differential equation to a submanifold. So let me make my differential equation a little bit different. So my submanifold doesn't look so good. And one chooses a submanifold, in this case a circle, and projects the vector field onto the tangent space of the circle. And that's going to give you a differential equation on your submanifold. And that's the essential idea, that we hopefully reduce the dimensionality by restricting to submanifolds. This picture here makes it look plausible that might work. If I'd chosen that as my submanifold, it of course would look completely implausible that the method would work. Approximating the manifold is going to be terrible. In the situation we're looking at, we've actually got an infinite dimensional problem, so it seems quite ambitious really to take an infinite dimensional problem, reduce it to a finite dimensional submanifold, and then hopefully, by projection, we'll end up with a neat solution. So that's the basic geometric idea. Okay, so I've shown you that. Yeah, so we end up with a finite dimensional equation. That's the goal. The first thing we have to do then is to choose a good submanifold. And there's a clue there, which we can get by solving the linear equation. And the linear problem actually has a well-known solution. It appears to be infinite dimensional, but actually it's just two-dimensional. If the initial distribution is Gaussian, it remains Gaussian from then on. So the diffusion keeps it Gaussian, the measurements keep it Gaussian. So to combine together, we'll always have a Gaussian distribution. So we can reduce that to an ordinary stochastic differential equation with just two variables. So for the linear problem, the dimension reduction works. And that's called the Kalman filter. It's well known, and it's widely used. And any problem can be linearized, so one ends up with the extended Kalman filter. And that's a fairly standard way of solving filtering problems. So this kind of gives us a clue as to what might be a good manifold. and that would be the perhaps the manifold of normal distributions. So maybe there's a chance that things will, if we project onto that manifold, things will look good. And indeed, one can do that, and it works rather well. It works better than the standard version of the extended Kalman filter. Unfortunately, if you represent the probability distribution as a normal distribution, if you choose that submanifold, we can only represent distributions with one peak. So we want to try and start choosing some manifold that allows us to represent multimodal distributions. And there are essentially two obvious choices. One very obvious choice is a mixture of Gaussians. The other choice, which will be perhaps the natural one at this conference, is the choosing an exponential family. Well, in fact, the exponential family has been looked at before. It works, the whole system ends up working quite well, but there is a problem in terms of the efficiency. So what we're really looking at today is the case of looking at a mixture of Gaussian distributions and projecting onto that manifold. So we need to choose a manifold as part of this program. We also actually need to define what on earth we mean by projection. Without a metric on the space of all probability distributions, it just doesn't mean anything. And there are lots of choices of possible metric. One natural choice, again, like this conference, would be the Hallinger metric, or essentially the Fisher information metric. That gives you, that's coordinate independent, so if you reparameterize your problem, you'll end up with the same projection. Works really fairly neatly with exponential families. But it has a problem, and that's you end up having to do lots of numerical integration, which kills really the purpose of it, which is to be fast. Another alternative is to define a metric between two probability distributions, say P1 and P2, which is the integral P1 and P2, just the direct L2 metric. And that's what we're going to use to define projection today. And the big advantage of that is that the integrals that will appear in a moment can all be calculated analytically. Okay, the picture I drew for you over there, involving vector fields, is very nice for differential equations. And it's an accurate picture of what's going on for differential equations. It's not really as accurate for stochastic differential equations. So I've kind of hoodwinked you with that picture. And it's relevant for the definition of projection. The stochastic differential equation I wrote down is actually shorthand for an integral equation. So this kind of differential equation, what it really means is you have to put integral signs in front of everything. You get an equation of this form. And then that makes sense, so long as one can define what integrating with respect to a noise term means. And there's a standard definition for that, the Ito integral, which I've given here. And this is kind of what I would think would be the obvious definition for integrating with respect to a random noise. So you sum up the value of the function against the difference of the function over small time intervals, and then let the time interval shrink to zero, or let the number of points tend to infinity. So it's very similar to the sort of definition of integral one which you have for smooth functions. There is a little area here, though, where I think there's a bit of a choice. Why have we chosen the time point ti and integrated that? So the interval, the times between ti and ti plus 1, which is the first value of the function. But it's changing throughout that time interval. We could have chosen any value. And so you end up with another alternative definition for a stochastic integral, which is called the Stochanovich integral. And all the changes that you start, instead of evaluating the function at ti, you evaluate it at the midpoint. That change in the definition of an integral makes no difference for smooth functions, but it's absolutely crucial in the case of stochastic differential equations. And one can phrase any stochastic differential equation either using Ito integrals, as we saw before, or these Stochanovich integrals. A major difference between the two formulations, though, well, there are two key ones. In finance, the Ito SDs are used much more because they're essentially causal. The fact that we evaluate the function at the beginning of time rather than midway through means it can't use information that occurred later on. Stochastic equations, on the other hand, transform under a change of variables according to the standard rules of calculus, whereas Ito's differential equations transform according to Ito's rule. The effect of that is that if you naively take a stochastic differential equation, treat all the coefficients as vectors and project them, then you'll get a different answer every time you do that with different parameterizations of the system if you use the Ito integral. Whereas if you follow this naive recipe of just write everything out as vectors, take all the coefficients, project them, that's actually invariantly defined so long as you write all your differential equations in Stochastic form. Okay, so the end result of that is we take the Cushman-Stochastic equation I wrote before, use a standard formula for projection, and we get this nice ugly equation. Well, I think I'm just showing it easy to prove. I've done some work, really. Let's move on and show what happens when we try and simulate it. So the one thing I want to say, actually, is that we've got these inner products. So these inner products are L2 inner products, and those are integrals. So when I said before that the integrals that occur can be done analytically, it's these integrals here. So long as all the coefficients in our problem are polynomials, and we can assume that by taking Taylor series, then all of these integrals can be calculated very practically. And that's where the Hellinger-metric and the exponential families fall down. So, what we have there is a finite Stochastic differential equation, and we can now solve this numerically. Solving stochastic differential equations is a bit fiddly, but there's a standard reference for it, and the same very specific numerical technique we use as the Stochastic scheme. But taking everything I've said there together, we pretty much have a recipe for solving the problem. One more detail we need is that although the differential equation is independent of the choice of parameterization, when you discretize a differential equation, the difference equation that results depends heavily upon the choice of parameterization. So one needs to choose a good parameterization of the manifold that we're projecting onto. So although I defined earlier the family of normal mixtures using a very obvious parameterization, one has to use quite an elderly one that ensures that the whole of Rn maps onto M, which is as large a coordinate space as possible. Okay, so let's just finish with an example. It's as simple as one can get, a quadratic sensor. So we just have essentially random walk x, and we measure it, but our measurement isn't linear, it's in x squared, so we only get information on the magnitude of the position, we get no information on the sign. What do we expect? If we know the initial state, we expect that as it goes through the origin, we'll suddenly lose track of the sign. So expect the probability distribution to become bimodal. That's what we expect. So let's see what happens. Here's the result. So the exact situation is this green line here, which you can't, this is in the initial state, you can't distinguish this from the red line, the two are the same. And then we're also plotting, pink and blue are two competitors for our method, but green is the method I've been discussing. Sorry, green is the exact filter, red's the method I've been discussing, and the other two lines are competitors. And let's watch what happens over time as we follow the simulation. So the competitors can't necessarily represent the exact state. That's why they're inaccurate at the beginning as well. But that becomes unimportant. So as time moves on, one can see the red line and the green line remain extremely close at all times. do then move it apart again a bit here. So we've sort of slipped off the manifold. But you'll notice that as time moves on again, it seems to repair itself rather. And that the expected behaviour that towards the end has become bimodal distribution. Here are some sort of empirical measures of the accuracy of the different methods, and you can see this is just measuring the L2 norm of the error, and you can see down at the bottom this red term is how the method I'm describing works, and it's like beating its two competitors reasonably convincingly in this case. So I think I'll end there.